access something sensitive so that I can speak. But I think that's okay. Okay. No, that's fine. Uh, Good evening, everyone. Uh, I'm Sreenidhi Nair, and I'm gonna give a small walkthrough kind of thing. Uh, I work at Byte Ally, and we are Haskell and mobile consultants. And currently, we are building a compiler which converts Haskell code into you know the mobile language like Java, C Sharp, and all that stuff. Right. Before I start, I just want to say that I'd like to have an interactive session. So there's going to be a lot of typing. Um, if you have a doubt, please feel free to interrupt me. And if you're having a laptop, probably it might be nice to open up the GHCI, the REPL for trying out Haskell. Good? Can we go forward? Okay. Uh, Haskell is a pure functional language. Um, it is statically typed, um, and over the few years, Haskell has been gaining prominence in a lot of places, including companies like Facebook. So they have been starting to adapt Haskell. So what's Haskell all about? It's just lambda calculus, type classes, and some sugar. Uh, I go into each of them in detail. Uh, yeah. So that's what Haskell is basically. So it's just lambda calculus, type class, and some syntactic sugar. Right. So what is lambda calculus? I don't want to scare anyone of you. It's a very simple concept. Uh, so all you have in lambda calculus is a var, a lambda abstraction. So that lamb has to be read as it takes an argument x and then it returns that x. And then an application. Application is just applying a term to another term. So this is the basic lambda calculus. So all it has is a var, an app, and a lamb. And we'll soon see how Haskell is very similar to the core lambda calculus. Uh, yeah, the next thing is types. Uh, I told earlier that Haskell is a statically typed language, which means every expression has a unique type. Every expression has a type. So you cannot have a expression without a type, and that type is going to be unique. Uh, yeah, I think I will jump into the REPL. So you can use. I'm running a REPL. It's called GHCI. You can run. When you want to try out something very quickly, you can start the REPL and you can type things in. So I just want to show you how to check the type of any given expression. So how you do it is by having colon. Uh, you could have any expression. So C has type car, and uh, so there's true which has type bool. So any expression that you take, it has a unique type. Uh, yeah, another example is hello world. Uh, so it has type list of car. This is there's a small thing I need to tell you here. Strings are represented as list of characters in Haskell. But in production, nobody uses the string. Everybody uses text. So, but for demonstration purposes, I think this is much more easier. Yeah, so you can use colon T to see the type of the expression. Right. Uh, so we have seen that every expression has a type. Similarly, functions also have types. And how you write the type signature is this way. So when I say add int arrow int, it means int takes two arguments and returns a result. That's how you need to read it. And this is the definition for add. So as I said, we are taking the two arguments x and y, and what you have on the right hand side of the equality is the result of that function. So what I'm doing is I'm just taking this x and y and then summing it up. Yeah, and RHS is the result. Yeah, but there's a slight issue here in that all functions in Haskell are curried. So the concept of currying is that every function will take only one argument and returns one argument. So that's how currying works. So so the question is how to have add in the curried style. So if you look at it, I'm accepting one argument int, and then I'm returning a function which goes from int to int. So it's like add takes an argument and returns a function, which you can again take and apply. Uh, just show that over here. Yeah. So in fact, I will use the GXA for this. So we have the function add which takes into. So to demonstrate the currying, I'm going to use add 5. So what I'm saying is when I apply 5 to add, I'm going to get another function which I can store. Uh, let is how you can make bindings in Haskell. So I'm binding add 5 to x, and I'm going to apply the next argument, and I get 11. So this is so every function in Haskell is curried, but in practice you needn't look at it that way. You can always look at it as if it takes two arguments, but under the hood, all functions are curried. That's how they work. And there's one more interesting thing here. If you look at the signature of add, it is int to int to int. The associativity of arrow is to the right. So you have to read it as int to, the whole thing is another function, and then into it. But the application, function application. So function application is just you give the function name and argument separated by space. It associates to the left. So it is add 5 and then 6, not the other way around. Any questions till now? It's fine? Okay. So the next thing is how do you define a custom data type? So in Haskell you can define two types of data types. One is product type and another is sum type. So so this is an example of a product type. So it's like the thing on the left is called the type constructor. So coordinates is a type constructor, and the thing on the right of the equality is a data constructor. So in this particular example, coordinates is a type constructor and lat long is the data constructor. If you look at it, it's like lat long takes two doubles. So you take a lat long and you feed two doubles to it, and you will get a value of type coordinates. And the next thing is sum types. The difference between product type and sum types is that you're getting a choice in sum types. So a value of type primary color could be red, yellow, or blue. It could be any of those. But in product type, there is no choice involved. It's just that lat long double double. So that's a major difference between product types and sum types. So you get a choice in the sum types. I'm going to try out constructing some of these values so that I can show it to you. The first thing is lat long. 5.0 and 5.0. So it has type coordinates. Because lat long is a data constructor of type coordinates. Similarly, I can create values like right, which has type primary color, uh, yellow, which has again type primary color. Uh, I would also like to show certain other things. So we have already seen how coordinates work. I also would like to introduce the record syntax at this point. Uh, so user is written with the record syntax. So what that additionally gives you are those projection functions. So you have username, user age, and email with which you can project out the particular fields. I just constructed the value of it. Um, so it's like let user equal to user. So name is foo, uh, age is 20, and email is just foo@bond.com. Right? So this is a successful binding. And if you look at the type of user, it is a type user, whatever type constructor you have on the left hand side. Now I can use these projection functions. Say I need to get the name out. I can use username user, which gives me the name out. So one could use these projection functions to get this out. And similarly, you can use the record syntax to update these values as well. For example, uh, I have a user and I'm going to change the name of the user to Bar, and I got a new user whose username is Bar. So with the record syntax, you can project the values out as well as you can update the values. One important thing is, although I've changed that bar, we are not mutating that value. The record update always gives you a new value. So in Haskell, you cannot mutate values. So you always have to produce a new value. I'll be talking more on mutation later on. But yeah, so if you use record syntax to update something, you're not going to get a mutated value. Instead, what you're going to get is an updated value. Um, yeah, that's okay. Fine. So at this point, um, we have functions, we have basic data types. We're going to see some Haskell constructs with which we can write code, which makes use of all the custom data types and the functions that we have defined. So one construct is let, another one is where, and you have case, which is used to pattern match. Okay, this is a very simple example of let. Uh, so if you look at it, what is the function doing? It's sum of squares. It takes two input, x and y, and I'm going to square x and square y and then sum them up. That's what's going on here. So I've just separated the expressions by having bindings like x sq, which is a square of x, and y sq, which is a square of y. And then finally, I add those two things up. Uh, yeah. Uh, is that confusing? Is there anything? Okay, fine. So the same thing I can rewrite with where expression. Where statement. Where is not an expression, instead it's a statement. Whereas let is an expression. You can have a let in any place where an expression is expected. Uh, if you look at it, it's all the same. I've just moved it to the where clause. It's just I'm again creating the x sq and y sq, which stores the square of x and y. Right. Uh, so next we have uh, pattern matching. Um, Pattern matching is important in Haskell because that's the way you drive the evaluation. Haskell is a lazy language, so pattern matching is the way in which you drive the evaluation. Uh, I'll Okay, before we go there, I would like to define two more types. Uh, so the first one is an int list. Uh, so there are it's a sum type. There are two parts to it. The first one is int cons, which takes an int and takes another list, and the second one is int nil. So it's like the int nil part is the end of the list. That's how we can look at it. For example, I can create a list int cons 5, int cons 6, and then int nil. Right? So this is a two-element list. The elements of the list are 5 and 6. And when I'm done adding elements, I would put an int nil to say that that's the end of the list. So that's how I would construct a list. And one more data type I would like to show at this point is int maybe. So there are some points when you do not know whether you have a value or not. A very obvious thing that you could think of is the null check. So you always check whether there's a value or not by using a null check. Uh, in Haskell, you don't have nulls directly, but you can represent the fact that you may not have a value by using the int maybe. So again, you have two choices here. You either have a value in just, or you may not have a value, in which case you will have an int nothing. Uh, for example, yeah. So int just 5 has type in maybe, and this says that you have a value. So there's a value called 5. And the other case is int nothing, in which case you don't have a value. So the lack of value is shown by the int nothing, and when you have a value, you wrap it with an int just. So this is how you would express the fact that you may not have a value in Haskell. Right. Um, yeah. So we're going to see how pattern matching works. Um, so I have a function called int maybe. What it is going to do is it's going to take a default value and it's going to take that maybe value, the int maybe value. And what I'm going to do is, if I have a value inside int maybe, I'm going to return that value. If I don't have one, I'm going to return the default value. Fine. So what do? I do a case im of where im is the int maybe value, and now here is the pattern matching going on. So what I'm doing is I'm saying IM could be either of in just a val or it could be nothing. So if you have multiple cases, you stack them back, right? Uh, so what case gives you is a way to introspect that value. You're able to look inside that value, see what it is, right? So in this case, I'm looking inside IM and I'm checking whether it is in just and then a value. If that is the case, I'm simply returning that value. If that's not the case, which means I don't have a value, I know that no value exists. In that case, I'm going to simply return the default value. Right? That makes sense? We just run this and see. So it's like I'll just create a binding in just as in just 5, and then in nothing as sorry, it's in nothing. Oh, can't use it. Okay, what can I use? I can't use in because in is a it's a reserved word. You can't really use it. It's a part of syntax, so that's why we are having. Right. So I have two values now. Let's do it. Let's do it. It's supposed to be that I am equal to. Oh no. Okay. So I'm going to use int maybe. Int maybe. First of all, we just see the type of int maybe. So it's going to take an int. It's going to take an int maybe, and then it's going to give me back an int. So what does this mean? This means I have to feed it two arguments. One, an int, which is a default value, and other is a maybe value, the int maybe value. Right. So we wanna maybe, and I'll have my default as 0, and first we pass the int just case, the ij. So in which case I get the value contained inside the just. And the other case is INO, in which I'll get the default value back. So that's how the maybe int maybe function works, and that is how pattern matching works. So pattern matching is a way for us to introspect the value and see what's there inside that. Uh, any questions? Right. Uh, you could also write the same function in another way. We needn't use case. Instead, we can pattern match at the argument question, at the parameter question itself. Like so, in this case, what I've done, instead of having a case IM off, I'm pattern matching at the question where IM was there. So again, it's the same logic if you look at it. I'm checking whether I have a just or not. If I have a just, I'm just returning the value, and if I have an int nothing, I'm returning the default value. Okay. Yeah, so that kind of completes the basic Haskell constructs. So what we have seen to this point is how to define a function, how to give a type signature for a function, uh, how to declare custom data types, some Haskell constructs with which you can write meaningful functions like let, where, and case. Okay. So uh, this is quite a jump. Um, uh, I hope everybody has heard about generics. So this is something very similar to generics. So in Haskell there are two kinds of polymorphism which are widely used, I could say. One is parametric polymorphism, and other one is adder polymorphism. We'll see about adder polymorphism a little while later, but right now we're going to see how parametric polymorphism works, and that is very similar to how generics works. So, um, yeah, before that, I would like to show a couple of functions. So, assume you want to write an id function which takes an integer and returns the same integer, right? It simply takes it and returns it. That's it. It doesn't do anything more than that. So for every integer, for it to work, I'll have to write a signature like id int, takes an int and returns an int. In the definition, I'm simply taking that a and returning that a, right? But say I want to do this for bool too. I need a id kind of function which works for bool. So I need to write again id bool, takes a bool, and then returns a bool. So if you look at the definitions, they are all very same. There is nothing different about them. So what can we do? What we can do is we can abstract over the type. So I'm going to say I don't care about what that type is. Just give me whatever you want, and I'm going to give you that back. I don't care about what that type is, right? So that's what generics does as well. You don't care about what that type is, right? Uh, so if you notice the type signature, ID int and ID bool have signatures which have type constructors which starts with a capital letter, and for ID I've used the lowercase thing. So lowercase variables in type context means type variables. I don't care what that type is. It works for every type. It's a universal kind of thing. It works for every type. You give me whatever you want, I'm going to give you that back. It's as simple as that. And if you look at it, that gives you a bit more of a guarantee. You know for sure that if you give me A, I won't give you anything else back because I have no way to produce that A. The only way to produce that A is by giving you back whatever you're giving me. right? So uh, there's extra power coming in. You know for sure that this is the only thing that can work. And that's why a lot of people say that you can find a lot of information about what a function does by simply looking at the type signature of a function. In this case, if you give me an A, there is no other way I can construct an A. So all I can do is I can give back whatever you're given. A similar example is const. So what const does is it takes two arguments and it simply gives you back the first argument. Again, if you look at it, I'm taking A, I'm taking a B. I don't care what that A and B is, and I'm going to give you back an A. That's how const is defined. If you look at it, the only thing I can do with this program, which type checks, is return the first argument. If you try to return the second argument, it is a B and it's not going to match with A and it's going to fail right. So you know for sure that this is the only way you can write this function. Right. Yeah. So that's right. The other thing is, okay. Uh, So we have already defined a list which is int list, which takes an integer and then takes another list, or it may take nil. And we already seen how this works. But if you look at it, it takes an int, right? Which means I can use this list only for ints. I can't use this for bools, for class, whatever. So, what's the obvious solution? You might start creating a car list, a bool list, and it goes on. Uh, the same thing you could apply here as well. Why not abstract over that type, right? So, we're going to abstract over that int by introducing a type variable. So, instead of putting int and putting a, I'm saying I don't care what that is, but all elements of that list should be that A. You can't give me an A and then give me a B. That doesn't work. I'll just show that bit. So we have list, which means I can construct const B, and then we have nil, right? So this works. And if you look at the type of that, it is a list of car, right? So it contains elements of car. That's what it contains. And similarly, you could have true and then false, which gives you a list bool. But if you try to do something like this, it's going to fail. Why it's failing? Uh, so I've said that the type that goes in here should be A, but that A has to be consistent. You can't have int here and in the next bit you can't have bool. So it has to be consistent. I can, if you simply expand how it would have been, how that expansion would have gone on, it would be like const A, and then again a const A, and then say you would have had nil. Both the A's should be of the same type. You can't simply have bool over there and car over here. So obviously that's not going to work. So you have consistent values, but the thing is it works for any type as long as you consistently give that type, the values of that type. Right. Um, yeah, and similarly we saw some type which is called in maybe, which uh, said, okay, maybe I have a value of int or I don't have a value, as in int nothing. If you look at it, I've said it can work only over int. Even this also we can abstract over. We can make it work for any type, which is what we do over here. So you have a just name or you have a nothing. So I can have like Jesse, which is of type maybe car, and I can have nothing, which is of maybe. Now, why is that A? It is A because nobody has fixed the type signature. If you look at it, nothing does not have any trace of A at all. So the compiler always infers the most general type, which means nothing would have a type of maybe A. If you want, you can specialize it by giving a specific type signature, and that will work. Right. Yeah, before I go there, so we had seen a in maybe function in which we saw how pattern matching works. But the thing was that int maybe was specialized to int. It could carry only int values, and the default was also restricted to int. Let's say I want it to work for any type. I want to write things generically so that it works for any type. Uh, yeah. So this is how it is. So the same thing, instead of the default value being int, now my first argument b is a default value, and then I take a higher order function a to b. So when I have brackets within the type signature, it means it's a higher order function. So that a to b is a higher order function, which I'm passing to maybe, right? So and the third argument is the third parameter is maybe. So what I'm going to do is I'm going to check whether the value is there within the maybe. If it is there, I'm going to apply that higher order function, that f. So the value I get from maybe is going to be of some type A, and that function takes some type A and gives you some other type B, right? So, and I'm saying the final result should be B. And so what I'm doing here in the first equation, what I'm doing is I'm taking that higher order function. I'm seeing whether the value is there or not. So if it is there, I take the value out from just, and then I apply it. Since the value will be of type A, because just has A. So that what I have over here is going to be of type A, and the function is going to go from A to B. So you can very well apply that f to A, which gives you a value of type B. But there is a case that I might not have the value, in which case I'll simply return the default. That's why I have the B over there and I'm returning the default. Right? Um, yeah. Any questions till now? Uh, is it too confusing or right? Um, yeah. So Haskell is a lazy language, uh, which means so. I'd like to take an example here. It's like take two and then repeat five. So what does take do? You give it any list. Take n will take n elements of that list and give it to it. That's what take is. And what does repeat do? You give it any integer, it will keep on producing a list which has only that element. So it will produce an infinite list basically, right? Um, I'm gonna show that. So if you look at the type of repeat, it's going to take any A and it's going to return a list of it. I'm going to send a car and it has gone. It's an infinite list and it will go on forever if I leave it. Right. So now the question is, if I have an expression like take 2 and repeat 5, it will terminate in Haskell. Whereas if you take a strict language, it's not going to terminate. What is going to happen is it's going to evaluate the whole repeat 5, which obviously cannot compute, which it cannot complete because it's an infinite list. So it will keep on going over there. But since Haskell is a lazy language, it will generate only enough number of elements from that list, from that repeat 5, whatever it is. I'm gonna, I'll just show the definitions of take and repeat here, and we're gonna see how take and repeat works. So if you look at the definition, it's like uh, if it's if it's 0, I'm going to uh, return nil, and if it is non-zero, I'm going to pattern match on that value, and then recursively call take again, right? So um, let's see how that works. Okay. I'm gonna. So this is how you have comments in Haskell. The long comments. You put an open curly brace and a hyphen, and you close it the other way. Right. So you have take two and repeat five. Uh, so we need to see like which pattern it's going to match. So I have like take two and repeat five. Uh, so we need to see which equation is going to match. Uh, let's take the first one. So it's like take 0, which obviously doesn't match because it is 2 over here. So it's not going to match. So you can ignore that. So it's going to drop down to the next equation. The second equation says take I and then cons x-axis. So I told you earlier that pattern matching is the only thing that drives evaluation. So to match the second equation, you need to evaluate repeat A. Only then you can see whether repeat A matches cons x-axis pattern or not. Right. So which means now to match that, I need to evaluate repeat. So what's the definition of repeat? You can simply replace whatever is on the LHS with the RHS. So repeat A can be simply replaced with cons A, repeat A. But you know for a fact that A is 5, so we can simply replace it with 5. Right? Right. Now, if you look at it, it has matched the second equation. It is take I and then cons x-axis. It has matched that. So we take the right hand side of that. So you can replace whatever is here with the right hand side of that equation, which gives you cons x take 5 minus 1 then x's. But what is x and x's? If you look at it, it is exactly these two things, right? So x has to be replaced with 5 and x's can be replaced with 85. That's fine? Right. And we know for a fact that I is 2, so it becomes this way. And the important thing is, even though it is 2 minus 1, it's not going to evaluate right away, and it will just stay as a computation. It's not still evaluating. So we still have another take an I and some value over here. So you need to again go back and see what pattern matches. So the first pattern is take 0. If you look at it, you will have to evaluate this to match that pattern. It will be like cons 5 and then take 1 and then repeat 5. But again, it's 0, so it's not going to match again. So it's going to drop down further. So yeah, if you take the second equation, I will match with 1. Again, you need to see whether it is cons x-axis or not. So for that, the only way is to evaluate repeat. Let's evaluate repeat again. So it's like cons 5, take 1, and then cons 5, and then repeat 5. Right. So now it has matched the second pattern. Again, I can replace the LHS with the RHS. So that would be like cons x is 5 in this case, and then take I is 1, so it's 1 minus 1, and then x is again repeat 5. Right? So again, you end up with a take and then some argument to that. So again, we do the same thing. You go back to take, but this time, if you look at it, the first pattern matches. 1 minus 1 is 0, and we are matching the first pattern. So we're going to replace the RHS of the first pattern for this one. It's cons 5, and then cons 5, and then it's like take 0, repeat 5. So the underscore is a wildcard pattern. it's like ignoring that thing. You don't really care about what that is. I don't have anything to do with that. So I'm just ignoring that, and I'm saying if it is take 0, just return the end of the list. That's in it. So this will come out to be good, right? That makes sense. We just run it and see. Uh, so it's like take 2 and then repeat 5, and you get cons 5, cons 5. So the important point here is, even though repeat uh, is infinite, we still manage to terminate our computation, and we manage to get a result out of that. Had Haskell been strict, what would have happened is repeat 5 would have computed again and again, and just as it had blown up my terminal, that's it. The program would have gone into any kind of thing. Right. So that's the evaluation. Yeah. Before we move on, I'd like to show you two nice things with GXCI. You can use Sprint. So what Sprint can be used for is to see whether a particular value is evaluated or not. So let's say I say x is repeat 5. Sorry, let's let x is repeat 5. Had it been a strict language, it's gonna repeat that 5 again and again and again, and uh, having this binding itself is going to fail basically. But here I'm able to write that, and sprint shows you whether particular binding is evaluated or not. So you could use sprint x, which shows you an underscore, which means it's unevaluated at this point. Uh, Also, I could use like that's select, and then sprint x. So I'll force it somehow. I'll force it. Okay, I think I'm lost there. What about yeah? So since I'm giving something which is the value is already there, there is nothing to evaluate, and you can just do and be a sprint, and it's going to give you the value. So if it was unevaluated, it would have given you underscore. So unevaluated expressions in Haskell are called as counts. It's just a term. Um, right. And one more thing is we could use okay, fine. So there's a command called set pluses, which tells you the approximate amount of time and memory it is consuming. That's what that bracket is there below every expression. So I've set it already. You could set it to see uh, how much time a function takes and how much memory it's going to consume. It's a very rough estimate. Uh, yeah, so it's something that is nice to use when you're hacking up something, but definitely not to be used in product management. Right. And Haskell is an immutable language, which means you cannot simply mutate values like earlier we saw how record update worked. It produced a new value. It didn't mutate the old value, and you can't really assign to the same binding twice. Uh, Thinking that it's going to mutate that value, that's not going to work. It's just going to create a new binding, and yeah, updating a data type will always produce a new value. It's not going to mutate. So what does this mean? If you have an immutable language, the race conditions have gone off. There is no way you're going to have a race condition, which means thread safety is kind of free for you. So this is something that you get with any immutable language. Right. We have a quick walkthrough to recursion. So what is recursion? Recursion is just calling the same function again with different arguments. Uh, so if you look at this is just a function called length, which takes a list and it's going to give you an int. And the int is the length of that list. So whatever list you give, it's going to compute the length of that list. Uh, what I'm doing here is just pattern matching to see whether it's a cons, whether you have a value or not. If you have a value, just do a 1 plus and then again call the recursive function. And if it is nil, which means you don't have any elements in the list, which means you can return 0. We'll just quickly go through uh, it takes a list, which means I need to construct a list. Nil, and it tells me the length is 1. I can add one more element. Tells me the number of elements in that list is 2. So yeah, so what's happening? I'm simply calling length again, but with the rest of the things. Like I'm ignoring that first the element whatever is there in the list, and I'm just calling the rest of the list, and it keeps on looping till you reach the nil case. The important thing here is if you simply write it this way, there's a chance that your stack is going to blow off. It's a normal problem with recursion because for every call you pay the cost for a stack. So the stack gets built up more and more depending on the length of the list. So GHC is the Haskell compiler, the most widely used Haskell compiler, and GHC is brilliant enough to uh, optimize away the recursion if we are writing it in the tail recursive style. So what's the deal with the tail recursive style is you need to have an accumulator in which you keep accumulating the values, and at the end of the loop you need to return that value. You shouldn't be calling anything else in between. But that's how it needs to work. So if you look at it, I'm passing 0 as an accumulator because at the beginning the length is 0, and I'm creating a where statement here. So again, I'm going to pattern match on whether it is empty or whether you have elements on it. Uh, I'm going to call loop again, but this time when I call loop, I'm going to increment the ACC by 1. And at the end, when it's nil, I'm going to simply return that ACC. So this is how you write code in tail recursive style, and if you write it in tail recursive style, there's a chance that GHC might optimize it away to just a loop. Uh, yeah, obviously you don't have the looping statements like for and while in Haskell, so this is the only way you can go about it. So you will have to use some kind of recursion to go over the things and get things done. Right. Uh, but the thing is, getting the recursion right is difficult because of the lazy evaluation that's happening. So it is very much advised that uh, we use functions that are already defined for for getting the recursion done. So there are higher order functions like foldl, foldr, and the other guys which we'll see soon. If you use if you use foldl and foldr for the recursion, you're not writing recursion by hand, and you don't risk, you know, uh, causing other issues like you could potentially have a memory leak over here if you manually do the recursion. I'll just quickly show you an example here. So we have lentil, right? This So let's quickly see how lentil works for. So it's like cons 5, and then cons 6, and then nil. So which is just 1 plus lentil cons 6 nil, which is just 1 plus lentil nil, which is just 1 plus 1 plus 0, and then it evaluates to 1 plus 1, and then finally it. So that's how the evaluation proceeds. The problem is, you could see that 1 plus 1 plus 1 thing is going on that side. So if you have a very long list, the computation is not going to happen right away because Haskell is a lazy language, which means chunks get built up. So you have a huge chunk built up, and then you reduce it. So chunk buildup has a cost. It takes up memory, and you don't want chunk buildup. So there are problems when you write code, when you write recursion by hand. So it's often advised not to do that and use higher order functions like uh, folder and folder. I'll just show a simple example of length written with folder. So if you look at the type of folder, it's like it accepts a function. It's a higher order function. You can think of the B as the accumulator, and A is every value that that is contained in the list. So what is happening is at every point I am updating the Z, which is the initial value. So I'll just show you an example. So how length works is uh, my initial value is 0 because if the list is empty, the length is 0. And then for every element, I'm going to take that accumulator and I don't really care about what that element is, and I'll increment that accumulator by 1. And that's all. We are not really pattern matching explicitly on the cons and nil and all those things. Foldel does the work for you. And we have a function which is called find. So what find does is you give it a predicate. Uh, if an element in the list satisfies that predicate, it's going to give it back to you. If the element is not there, it's going to give you nothing. So that's how find works. Uh, so it works very similarly, except that I have used folder here. Uh, so there is like difference between using folder and folder, but I don't want to go into that right now because um, yeah, I just don't want to go into that right now. But uh, just remember that don't don't use Foldel. Try to use Foldel Prime, which is a stricter version of Foldel, and Foldar is uh, is better in case where you might gain something with lazy variation. I know it's all very abstract, but I really can't go through the entire evaluation right now, so I'm sorry about that. Um, right, so we have the go x rest, and I'm checking whether the predicate is matching. So if the predicate is matching, I'm going to return that value. So if the predicate is not matching, I'm going to go further. So I'll keep on going till the end. And at the end also, if you're not getting any value, you want to simply return nothing. So that's how find works. Um, we go to, yes, common use operators. Uh, does that look very awkward? The pipeline. Uh, so what's happening is I'll just have a, yeah, so that is word count. So two widely used operators in Haskell is dollar and dot. So dot is used for function composition. So you have a function f and you have a function g. You're gonna apply when you say f dot g, you're gonna apply g first and get the result from the g and then apply it to f. So that's what dot does. We'll see an example. So um, so let me have a function which um, okay, we just take this itself. I think this is so what is happening here is uh, you have to read it this way. Now they're saying that dot has infix r, which means it associates your right. Um, so the brackets go this way, and I've used something called as point free style over here. This is equivalent as saying these two are the same. I can simply ignore the argument if it is simply going to be applied at the other end. So these two are the same thing. So what's going to happen here is I have length dot some huge random function. I'm going to simply call it f for now, and then uh, the whole thing is bracket, and I have x. So this is same as length, and then fx, right? Now what is f? F is concat dot map dot words dot lines. So this goes. Uh, concat dot map words dot lines and then x. Again, if you keep on applying the same thing, what we're going to end up is with length, concat, map words, lines, and then x. So what does lines do? Lines is going to simply split a string wherever you have new lines. So it's like foo slash n, and then bar, I can have lines, and it splits into foo and bar. So map words is like it's going to split the sentences into words. So I could have a sentence over here, foo, and then another foo, and then bar, another bar. So lines, and then I'm going to do a map words because now I have a list of sentences and I want to do splitting on every sentence. So that's why I have a map. So map is something which applies a function to every element in a list. So now I have a list of foo, comma foo, and then bar, comma bar, and concat is going to join all of them up. So you have multiple lists. It's going to concatenate the list and give you a single list. And then at the end, I'm simply looking at the length of it. Yeah. So it's a lot of production Haskell code seem to have code like this. It might seem to be very awkward, but it's nothing but application. It's nothing. There's nothing more than that going on over there. And then there's one more weird function which is dollar. All it's going to do is it's going to take a function, it's going to take a value, and then simply apply it. Looks ridiculous, right? It's like ID. So we have all these in ID. So ID is a function which takes an argument and gives you back the same argument. Say I pass an argument to it, I'm going to get that back. So it's just like the function has been applied to the argument. That's all what's going on. Will I take one, so we'll finish it, right?
Every time of scenarios, 5 to 5 minutes.
Yeah, sure. So I'll just start by talking about type class. We have already seen how parametric polymorphism work. So ad hoc polymorphism is another type of polymorphism that Haskell supports. So what is ad hoc polymorphism? So it's just that you can overload behavior based on type. So I'm going to give a simple example for that. So there's this type class called show, with which you can get a string representation of the type. I can do a show on, we have defined types like user. So I can have user who and the age is 20, and then we have Tom, and it gives you a string representation of it. Another thing is you can use there's a handy command called :i, which gives you information about a particular entity. So I'm going to use :i on show. So there are a lot of things, but the most important thing is so this is a type class. It is parameterized over one type, and I'm just going to take this method alone for demonstration. It's like it takes a name and gives you a string. But the magic is I can overload. I can have different shows for different types. I can decide how that show should be for each type. So in parametric polymorphism, you are not able to say what you want to do for each type. All that we were able to express was it works for every type, but just one behavior. It's not many behavior. But what I can do with this is I can say how it should work for user. I can say how it should work for some other type. Uh, it's all up to the user basically. So we have the power to get different behavior for different types. So that's what I mean by overloading behavior based on type. And it's different from function overloading because function overloading is just a compiler trick. Uh, and it's different from, yeah, by compiler trick I mean internally they would just rename the functions, and then that's how function overloading works. And it's different from interfaces in sense that if you want to make a type, if you want to implement an interface for a type, you have to do it at the time when you define the class in the OOP language. I mean. That's the only way you can do it. Uh, but in type classes, I can define a type class later on and then give an instance for that. So there is an open world assumption in which I can give an instance way after the type has been defined. Uh, Right. I'll just show very quickly what these common type classes are. We have already seen show. So EQ is a type class which gives you equality. So it lets you to define how equality should look like. Uh, so for int, I would say that both values should be same. That's when it is equal. So you can give your own equalities by having instances for these type classes. Odd is a num class which is used to define ordering, to say which is greater than what and which is lesser than what. And num is a type class with which you can do arithmetic operations like plus. Uh, so we'll see num as well. So you have plus, minus, and multiplication, negate, and all those things. So which means you can have your own type and still get all of these operations by giving an instance for that class. I think we'll close here. Uh, there's still a lot to go, and yeah, we just wait.
Yeah, probably we'll do a follow-up of this
Sure,
one.
sure, sure. Is there any questions? Any doubts or anything? Good. Yes. Right.
An example like identity functions, those kind of things.
Yes.
It looks cool, but I'm not sure in an application perspective, right? Have you, in your experience, have you really seen it is helpful?
Okay.
Or comparing to some other languages?
Right.
You've seen this is better.
Okay. So as I told earlier, we are developing a compiler which converts Haskell code to Java or C# or whatever. Don't you think that's cool? Like that's something we are able to do. Don't you think that's amazing? I'm just able to take Haskell code and then convert it into any other language. That's what we're working on, and I think we are able to do it in a fashion that is much more superior to the other languages in terms of code size as well as expressivity. I think it's really cool. We're able to do a lot of things. But I'd like to dispel this myth that Haskell needs category theory to work with. You don't really need to know category theory. It's just that Haskell uses a lot of goodness from the category theory, and why not? The mathematicians have done a lot of work to reach where they are now. But why don't we use them so that we get a better language? It's just that you don't have to. It's not that you have to know about category theory. It's just that there are some concepts which are taken from category theory, which makes Haskell work very nicely. Yeah.
You see, one of the real life scenarios where Haskell
One place is Facebook has been started using Haskell recently.
I remember
Uh,
that exactly.
Right. So what they have built is a spam detection engine. They have completely used Haskell for that. I'm not sure the details about that. I've heard that they have used that, and in a lot of financial institutions around the world, Haskell is being widely used. Standard Chartered is an example. They are using Haskell for their internal, programming things. And our company is an example. I can give you much more detail about what we do. As I said, we are building a compiler right now. Just think about writing a compiler in a language like Java or C Sharp. I think it's daunting to me at least. And I think we are able to express what we want to say in much lesser code and more correctness. If you look at the degree of type safety that Haskell gives you, I don't think any of the modern languages reach anywhere near. The degree of type safety that we get is extremely high, and I think that's a huge thing, which lets us be sure that what we are writing is correct. I think that's a huge gap. Sorry? Yeah, sure. We are also building web apps along with that in Haskell. In fact, we have released a new package called Web API. If you want to try that out, it's on the public repository package. Yeah, you were about to say. I'm sorry. Sorry. Same stuff. Yeah. Anybody else? Any questions? Yeah. Ah, it's a real compiler. It's a real compiler which takes input as has written. Okay. The question is, yeah, sure, sure. Yes, yes, yes. So I'm going to give you an example. You want to write a mobile app, right? You want to write it in the Windows phone. You want it to run in Windows phone. You want to run on Android, and you want it to run on the iOS. So what would you prefer? Would you prefer writing three code bases for all of them, or would you like to have one and then generate code for all of them? Yeah, but you're not going to get the native code. You can do that, yes, of course, but okay, 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 right, okay. Right. The point is we are also able to do that. We are. I'm not denying that point. I'm just saying that we are also able to do that. And yeah, the original question was what could you use Haskell for in the industry? Am I right? Am I reading that question correctly? The original question. You were asking about the utility of Haskell. Right. Right. Uh, so you don't have the clutter of object-oriented programming. Can I put that? You only have functions. You only have application. You don't have anything else. You want to program the language where you have 100 constructions, where you want to have, you want to, would you like to have an environment where you have functions? The number of constructs in Haskell is extremely limited, which makes it easy, at least according to me, to read and understand what's going on. Frankly saying, I have been integrated by the loop languages. I tried learning them, and I'm still integrated by them. I find Haskell to be much easier than any of those. Maybe your perspective might be different, but probably you should try out Haskell and maybe it makes sense. Okay. 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 Could you tell me what is the real use case? Anything. For example, anything. Just. Okay. So you want a web app kind of thing? Okay.
forget about all the UI and UX.
Right, right, right. Fine.
Why would I have to write in Haskell? Why should I go to functional language?
Okay.
If I'm able to do the same thing in multiple languages, and every language sucks, it's we are going to achieve the same thing in different ways.
Right. I do agree that.
Detail something out.
Right. I do agree with that. But what do you think about working in a language which doesn't have null references, which gives you, which lets you write very strong types and make sure that your contract doesn't violate that type? What about things like that? It gives you much more guarantees. You are much likely, and you're much less likely to go wrong. So what about those kind of guarantees? Does that sound appealing to you? That's what you get by Haskell. You get a strong type system which you can leverage, which means uh, the the area where you go wrong comes down drastically. That's a huge win. You don't, which means that you can write code which is correct, and if you are wrong, the compiler tells you that you are wrong. I think that's a great win. The compiler is telling you that okay, this is not the way to do it. It's very difficult to get these kind of features in other languages, right? And I'm not sure. I have programmed extensively in Haskell, but not in other languages. So maybe I'm wrong, but I feel like Haskell gives you a very strong safety. The compiler itself is a safety net, which always saves you from fault.
Okay, so sorry to stop you. You're way above the time. Sorry for poor time management. So we can continue the conversation
Yeah,
over
sure.
over dinner.
Sure.
So before we break for dinner, we have